sorry. So we have 3 parts left. Let's start by part 4. So what we did before the break was we looked at when backchannels should be produced or could be produced, and then we tried to generate this ourselves. And we had some perception experiments. Now we're gonna combine those into one framework. So first, some preliminary work. So just a couple of slides about multilist corpus that was recorded by Ivan, and that was a little bit presented yesterday in his slides and also in his poster. So you might have seen that. So I'll really quickly go over it. So what he did was he had 1 speaker and 3 listeners at the same time. So there was 4 people engaged in the conversation. They were all at different sites, and they were recorded, and they could see the other at the same time, and they were paired. And actually, all the listeners could see the speaker, but the speaker saw only 1 listener. And the aim of the corpus was to find out, in an online setting, whether people, listeners, would produce nods at the same time, or if there would be variability. So this is the idea. You see at the bottom 3 listeners, you see 1 speaker, and the speaker only sees the middle listener. So they all think they are interacting with the speaker, but only 1 actually is doing that. So this is a small clip. It's in Dutch, so it's hilarious.
Ik heb een filmpje gezien van Looney Tunes. Het heet Tweety in the Canary Row. Tweety in the Canary Row.
Okay, so if you look at this, then you see that there is quite some difference in when the 3 listeners, so those 3 will produce nods when they will say
zoals altijd. En dat gaat hij op verschillende manieren proberen. Ik ga eerst even proberen al die manieren te herinneren. De eerste was dat hij via de regenpijp omhoog klom. Naar het raam waar de kooi van Tweety stond. Het tweede was
okay, there should be
dat hij door de...
So you saw that the guy on the right top, he was nodding a lot, and the others were doing not so much. So you see that there's a lot of difference between those. Actually, the guy was explaining how Sylvester, the cat, was trying to catch Tweety, which is a very strange thing to tell, but still. Okay, so one of the things that we... first, really shortly. So there were 32 listener interactions, and there were almost 3,000 back channels, and you see here that there is some spread. So there's a lot of moments where only 1 listener would produce a back channel, and you see basically the same pattern as with parasocial consensus sampling. So remember that we had those things before. So you see there's quite a lot of variation. So the lessons learned not only from multilist, but also from parasocial consensus sampling, and also from the yugs that we had, is that there is no full agreement what good moments are to produce a back channel. So there's a lot of subjective variation there. But it seems that some places are better or more appropriate than others. So still there is something that we can learn there. Also quantity, timing, and type affect how it's being perceived. So back channels are optional. So there is no true right moment to give it, but it might be better than others. And also there might be no real bad moments, but some might be better than others. So we're going to look at this, and this is an important notion. So what we're going to do right now is we're going to combine everything that we did before. So we're going to make a generative model, so a prediction model that can predict the timing better. And with better means that we have better subjective evaluation. So the perception, the human perception should be better. And we have some constraints, so we want to keep the quantity and the type fixed. So we don't want to look at different types of back channels. We're only going to look at nods. We're going to keep the quantity, so the amount of back channels per minute also the same. So our approach is to have an iteratively refinement of a machine learning model. So we're going to learn a model, evaluate it, then refine the model, evaluate it, and refine the model. So it is iterative. So that's how we're going to get better models every time. And this is what we termed iterative perceptual learning, just because we thought it was a nice name. Very quickly, because Fernando has told you everything about it, sport factional machines have some very simple things to say about it without any equations. So if we have a two-class problem, in our case we have good moments to produce back channel and bad moments to produce a back channel. We can use support vector machines. And if we have training vectors which have corresponding labels, so good and bad, then you can train a support vector machine, and what it will do is we'll make a hyperplane in the n-dimensional space which tries to separate the two classes. Then if we have a new test vector, so a new moment in time, we can see if it's on either side of the hyperplane, and if it's on one side we say it's a good moment, and on the other side we say it's a bad moment. In addition, we can look at the distance to the hyperplane, which gives us a sort of a measure of confidence. If it's really close to the hyperplane, then we're not so sure if it's a good or a bad moment. If it's really far away, there might be a really good moment or a really bad moment. So it looks a little bit like this. So this is in the training phase. We try to make a separating hyperplane. You see that one of the green dots is not at the right side, but it's not a problem because there's always noise in your data. Okay, support vector machine work on individual samples. So they take one frame and say it's good or bad. They don't take any temporal features into account. So that is a good thing, because if we can classify each individually, each sample, we don't have to have so much data. We only take all the back channels, we take some negative examples, we can learn the hyperplane, and we're done. There's also disadvantage because we don't model the temporal characteristics of the time and of the back channel. So we cannot say, hey, in the 100 milliseconds before this happened, so now we should produce it. There's a solution to that, because we can encode time in the features instead of in the model itself. And that's exactly what we're going to do. So again, we're going to look at prosody, we're going to look at speaking, and we're going to look at looking, gaze. Prosody, we're going to use 112 dimensional vector. Speaking is binary, and looking is also binary. So for pitch, intensity, and MFCCs, I think you heard everything about it this morning. And if not, you will hear about it tomorrow. So I won't go into that. And also we're going to use different windows. So we're going to use the mean of these features over the past 50, 100, 200, and 500 milliseconds. So that's how we encode time into our samples and into our features. And for speaking, we do something different. We're going to look at the number of frames that have passed since the last time a speaker started speaking or stopped speaking. So, for example, if he stopped 5 frames ago, then we say it's -5. If he just started 5 frames ago, we're going to say it's +5. So it's basically an offset to that moment. And we do the same with gaze. So we're going to look at the time between the start of the gaze to the listener. Okay, so back to the optionality of backchannels. So if we have support vector machines, what we need to do is we need to train them with a set of samples. Some need to be positive, some need to be negative. So we have a 2-class problem, and we have to provide samples of either. But then we have a problem, because we have positive samples, which are the right moments to provide a back channel. And we know if we train this from a corpus that they are right. But then again, for the negative, we don't know. Because if we take moments in time where no back channel was produced, there's not a guarantee that if there will be one produced, there will be a bad idea. So we don't really have negative samples. So if we're going to apply a support vector machine, some of the negative samples might not be negative at all. Okay, so what we're going to do is first we're going to learn a baseline model, and then we're going to introduce what we did to solve this problem. So what we do is we take the corpus data, we find the positive samples, so that's the samples that correspond to when a back channel was being produced, and the negative samples, which basically are sampled at moments where no back channel was produced. Then we learn the SVM, and finally, if we're going to do this, we apply the SVM to new test vectors. So we're going to take another sequence of a speaker, going to calculate the features, and at each time moment we're going to apply the SVM, and we get a score out of it. Well, we put a threshold on the score because we don't want all the samples to be important, and then we do a per frame score, and all the ones that fire we think are interesting, and then we mask in time. So we have a rule that there should be at least 1 second between consecutive back channels. So usually if you have a good moment where you could back channel, then this fires a lot after each other because you get high values because the features are encoded in very much the same windows. So these kind of thresholds are being used. So eventually what we have is we put in a new sequence, calculate the features, and eventually we get out discrete moments in time where a back channel should be produced according to this model. Okay, one of the things is that we should adapt the threshold to obtain the optimal number of back channels. So our constraint was that it was fixed, and we do this only offline. So that's the only way that we can really say with this threshold we get exactly 8 frames, back channels per minute. So the baseline model looks like this. This is a little part that will be shown in some slides further, so I'm going to explain this very shortly. So we have videos of listeners and speakers. We extract the moments in time that correspond to positive samples, the white ones, and the gray ones, which are the negative samples. Then we learn a model, and eventually you have a circle, which is a model. Okay, then what we need to do is evaluate what we have done. And we saw before that we have several measures to do it. We have the objective measures, so we can use precision recall and F-score. And later on we looked at subjective measures, so we need to animate the video. And then we place them side by side, and then we can use our perceptual evaluations, such as the ratings that we did from 0 to 100, or we can use the YUX and use that as a measure of inappropriateness. So these are the 2 different types of evaluation that we can do in this type of research, and we will do both. This was the scheme that we saw many times before. So if we use the YUX here, then that is a measure of inappropriateness. And that means that there are bad moments to produce a back channel. And if you look at that, we can actually use those as negative samples to retrain our model. So instead of having the semi-negative moments that we use from the corpus, we can actually use the real negative moments as supplied by the YUX. So that gives us negative data that we can more sure about that's really a bad moment. So based on the subjective output, based on the perceptual evaluation, we can retrain our SVMs and just see what it does. Retrain, and there's the interaction again. So it looks a little bit like this. So the scheme is a little bit adapted. We start with a human speaker who's being observed with camera and microphone. His video is put here in the stimuli. At the same time, we have a model that predicts what to do based on these features. We animate the virtual listener. Then we have a lot of people look at the stimuli. We get real positive and negative examples out of it. We retrain the model, apply it, and we have a loop here. So we get increasingly better predictions, we hope. And that's what we're going to find out. Okay, so from a processing point of view, we start with a bootstrap because we need to start with something. So we start with the gray samples there of the bootstrap. And then each iteration, we have 3 phases. So we have generation, we have perceptual evaluation, and we have model learning. So we start every time with getting the features out of the speaker's video, applying the model, getting stimuli, having them judged by people, getting the samples, retraining the model, getting a new thing based on the video. So this iterates, and every iteration you hope that the samples get more specific. Okay, if we're going to look at generation, we're going to do the same as in our previous studies. We're just going to animate the virtual listener, put it side by side. We use the alkalic animation platform, and this time we only show not, so we're going to not going to look at type. Okay, timing is based on SVM output, and we stick to 7.7 back channels per minute. And we can do this because we do this offline. Okay, then we have several human judges, human subjects, judge every sequence, and we used 5. And they provide YUX as before for all the moments that they thought were not appropriate. And we match those to the actually performed back channel, so we know for each back channel how inappropriate it is. So then again, each YUX is considered a negative sample, and if a sample got more YUX, then we put it more often there. So we put more weight on it. So instead of giving weights in SVM, we put in the sample multiple times, just as a same measure. And as a positive measure, positive sample, we use all the back channels that have been performed by the listener. And we do the same thing there. So instead of using the exact moment, we sample around it, so we get a better spread of what happens in the video. So there might be 250 milliseconds before or after, and we make sure that 95% of our sampling is in that region. So we get more variability there. And eventually, we're going to train the SVM with a balanced number of samples. So we want to keep the number of positive and the number of negative samples equal, so we can just get good results out of it. So we use the multilist corpus as our data here. We did 4 iterations of EPL because it takes a lot of time to evaluate, and after 4 we get bored. And in each iteration, we retrained the model on a separate test set so we could compare it with a baseline. So we had the iterations, which got us samples, and then every time we also had a separate set so we could compare the performance on the test set. Okay, as before, the baseline model is trained with positive and negative samples from the same training videos. So EPL and the baseline model used exactly the same amount and type of data, so we could compare them directly. And then again, negative samples were just sampled at the non-positive points. And 5 subjects looked at each of the videos. So these are the results. We did 4 iterations, and EPL and the baseline model were exactly the same in objective measures. So we calculated the F-score, and it was exactly the same, and it was not that bad. But then if we look at the average number of yucks per back channel, it was slightly different, not too much. We saw there was 1 for the baseline model, so that means that from the 5 people that watched it, on average 1 would say that it was crap, and it was slightly lower for EPL. So there's a slight difference there. And then if you look at the back channels that did not receive any yuck at all, then it was 5% higher for EPL, which could be a sign that this perceptual thing actually is slightly better than using the baseline model directly learned from a corpus. One of the things is that in each iteration we use more training data. And usually if you use more data, your model gets better. So we wanted to see if this actually happens. So what we did was we looked at all the test sets after each iteration, and we looked if there was an increase in F-score. And you see that at start there is this increase until the 3rd iteration, and then it drops. You see also that it tends to be saturating, but then still it drops in iteration 4, which is kind of strange, and we're going to look into that. So apparently the F-score does not always increase with more training data, and how does that come? First we're going to look at the subjective measures. So if the precision and the recall drop, does this also mean that the perception is getting lower? And it is not completely the case. So you see that there is an increase from 1 to 2, and then it's decreasing. So you see that the subjective measures and objective measures are not completely correlated. So that means that the behavior might be perceived better or worse, even though the objective measures say differently. So it's interesting to look at these numbers, and also you see that they are much more closer, which is also informative. So what could be the reason for the fact that more data will not give you better results? And it might be probably different in conversations. So what we did was we trained the model after the first iteration and applied it to all the others. And you see that the 3rd iteration gets better scores, and then the 4th iteration gets worse scores. So there could be a sign that the 4th iteration contains conversations or speakers that are much more difficult to model, that show different behavior than all the others. So our model that we are learning does not really match to the videos that we see in iteration 4. So some conversations have different characteristics, and eventually, since we are also using these training samples from these conversations, that means that we're also using these in our model. So it also affects training. So what we did was we combined machine learning with perceptual evaluation. So we did the 2 things that we did before the break, and we introduced iterative perceptual learning. Even with same scores, we can have a different perception. So it doesn't mean anything if we get good scores in objective measures that might be perceived differently. And we used pure negative samples to improve the perception. And we also saw that more training data is not always better. And iterative training also allows us to find out what is a good moment to stop training, because then we can see if training data saturates or get even worse. So we can see, hey, we can stop now. We don't have to use any more data. There are also some limitations of the study. So first, the features that we use might not be informative enough. We got saturation quite easily. So it might be that there is not enough information in the features that really allows us to use a lot of data to get it out of it. We learn it quite quickly, but then we stop at the point that is suboptimal. So the features might not be interesting enough. Also, we had to set the threshold for the things offline. So this kind of study we could only do by offline setting a threshold and then only generating behavior for a whole fragment. So that also gives limitations if we want to apply this kind of work in an online setting. And there was no adaptation to the subject. There were some conversations that were really bad. There were some that were actually quite good. Probably the bad ones could be dealt with if we could do some adaptation, probably with the threshold. And there were only nods, and we didn't do any vocalization. So these are limitations that we should address. So this is the final part of the practical work that we did. And that was, we wanted to apply the work in an online setting. So everything that you saw right now was offline. People have been looking at videos, or we looked at corpus and just calculated characteristics over it. So this is the only part where we actually move this to online settings. So we actually had people talk with virtual listeners. So the motivation is that we used videos before, and that had some advantages because we had good stimulus control, but obviously eventually you want to have online. And the disadvantage of using offline is that we don't have contingency. And contingency is the fact that there is continuous conversation going on. So if the listener does something strange, then the speaker usually reacts to it. If the speaker does not, for example, if the listener does not give a nod at an important moment, you would expect the speaker to stop talking. Also, if the listener will be saying, you would expect the speaker to frown and to stop talking or ask whether the other is all right. So we don't have that here because we don't control the speaker but only the listener. And in an online setting, we can. So the solution is to do online experiments. And that's exactly what we're going to do right now. So most of the things that we need for online, we already did. So the features that we extracted, they can be extracted in real time, which is important. There's only a minimal delay because we use the windows. At the same time, we have support vector machines, which can be evaluated really quickly. So they are fast models, and they can be used on a per frame level, per frame basis, sorry. And also we have an animation platform that can perform these behaviors, the nods and the ahas, with minimal delay. So these three things, the observation, the modeling, and the generation, all can be done really fast. So that's important so we can have a real-time conversation. So one of the two challenges that are remaining is the setting of the threshold. We saw before that we did this offline. So we had to calculate everything, try different thresholds, and then see which one worked best, which gave the optimal number of back channels. We cannot do that now because we don't know what's going to happen in 1 minute. So what we did was we normalized all the features using z-scores. So we subtracted the mean of each feature, and also we made sure that the standard deviation was 1. And we did this because we recorded a small sample of each speaker beforehand. We just had 15 seconds of speech. We normalized all the features based on the mean and standard deviation. Another challenge that's remaining is the evaluation. Usually we just have people look at it and then yuck it or just give a rating. In an online setting you cannot do it because it disrupts the conversation. So we had to come up with a new paradigm to evaluate online conversations. So what we did was we looked at what we did before, and one of the things was that humans just gave really terrible ratings to videos, even though they were produced by actual humans. So if you remember the copy condition from previous experiments, people would still say, yeah, this is just bad. This is not a human, even though it was performed by a human. So to solve this, we actually, okay, the reason for that is that there is only limited variation in animated behavior. There will be only nodding. Maybe you add some blinks, but there will be only nodding. So people would just say, this is not a human who does this. So we're still aiming for this systematic control, but we don't want to have this bias that people always say, hey, this is not normal because there's only this animated. So our solution is to have both a human listener and an algorithm at the same time, and then give them the same expression capabilities. So make sure they can perform the same behavior. So that means that we have a human that might be nodding, and we have an algorithm that might also be nodding. They should look the same. They should be able to do the same kind of behavior. Okay, so what we did was we came up with a switching wizard of Oz, and it works this way. We have a speaker and we have a listener which are not in the same room. Similar to multi-list, the listener sees a video of the speaker. So the speaker is talking, he's being recorded, and the listener can see that at the remote side. The other way is different, because the speaker sees an animated version of the listener. So he doesn't see the actual listener, he doesn't see a video, he sees a virtual listener who's performing the virtual behavior. And each time the listener will perform a nod, he presses a button. So that's a current limitation, but it works quite well actually. So there's a speaker at this side, there's a listener at this side. Every time the listener will produce a nod, he would just press a button. What happens is that the button press is being translated and a virtual listener would nod. So they can have a conversation like that. So basically the listener by key presses steers the virtual listener. So this is the side of the speaker. Speaker will be sitting here, would look at the mirror. You see this is a mirror. There will be a camera behind it, it will be recorded, that will be sent to the listener, and the virtual human would there be displaying the listener behavior. At the same time as the listener is pressing his buttons, we also have an algorithm working. And the algorithm works with the features that are extracted from the speech of the speaker. So we look again at speech pause, we look at intensity, and we look at MFCC features. Again, we use the windows, this time of 100, 200, and 500 milliseconds. So that's how we encode what's going on in the speaker's speech. And we have our algorithm running. So we have an SVM, which was trained beforehand. We classify everything that comes in, we set a threshold, and we apply it, and then we produce a nod every time it's above the threshold. So that's quite easy. So we have, at the same time, we have a human pressing buttons. We have an algorithm saying, hey, this is a nice moment to do it. And what we do is sometimes we show the button presses of the human, sometimes we show the nods of the algorithm. And then we change them at random intervals. So this switching happens, for example, every 30 seconds, or maybe 20 or 40. The speaker does not know. So the only thing he sees is nodding. And sometimes it's from one source and sometimes it's from the other source. And he does not know when this happens. Well, since nods are discrete events, we can easily switch between them. The only thing that we have to make sure is that no two nods would be closer than 1 second together. So we can interpolate between them. So if we would switch from algorithm to user, no one would notice because it's only nods that we generate. And then what we did was we asked the speaker to press a button whenever he thought that the behavior of the listener was not from the human, to press a button. So there would be a moment in time that he thought, hey, and now it's not okay, and then he would press a button. And every time he presses a button, it's automatically switched back to the human listener. So he would have a conversation with the listener. Usually, the better the algorithm is, the less he would see when the switching will be there, and every time he thought, nah, now it's not okay, he would press a button, and it would switch back. So the advantage of this kind of paradigm, there are several. So the human and the algorithm have the same capabilities of expression. So you would not have a bias because you're not animating all the behaviors. So you really have to make sure that you don't press a button when your friend who's at the other side is just pressing his buttons, and you would say that he is not human. Another thing is that we don't have a bias due to this. The third one is that we can look at the behavior in terms of quantity and also the timing. So we don't have to look per se at certain conditions. We can take all samples and see when does he think it's not realistic, when does he think it's not human-like. This might also be when a human is actually performing all the nuts, and we will see that this actually happens. Also, we can look at longer-term behavior. So we're not looking at individual back channels, but we can look over a certain amount of time. So maybe one back channel can be wrong, but if it happens twice, then he knows, hey, this is not a human person. And also, since we're collecting data at the same time, we can retrain our algorithms with that. So we're constantly collecting, because we constantly get key presses from the listener. So this gives us a lot of data, so we can retrain and even adapt. Okay, this is quite a complex scheme here. This is completely symmetric. We use a different version. The idea is as follows. We have one speaker here who's being recorded again. So his data is either going directly to a switch, and his virtual self is animated for the other person, or we have a model that predicts what should be done. This is also going to the switch, and he sees it himself. So the inner loop here is the algorithm. The outer loop is the key presses. What we did was we had only one loop, so we had only one speaker, and the other one would just see the video. In our experiment, we had 12 pairs of subjects. In every pair, there would be a speaker and a listener, and halfway they would switch. And they would be talking about random topics, their family, food, holidays, hobbies, everything. I think also what they would bring to a deserted island. Every conversation lasted on average for 8 minutes, so we really had to make sure they kept on talking. So these were monologues of 8 minutes, and after a while they got just ran out of topics or just got bored, and then we stopped the recording. So the virtual listener eventually was operated in 6% of the time, and this is more than half because it automatically switches back to the listener. So that means in 60% of the time the speaker was looking at the key presses from the human listener, and in 40% of the time it was looking at the key presses of the algorithm. If we look at the number of times the speaker thought behavior was not realistic or not human-like, from a total of 138 yucks, there were 96 during the algorithm, but still 42 during the human listener. So 42 times when an actual human was pressing the buttons, the speaker would say that it was unhuman. So that's quite surprising. And also, if you look at the percentage of segments, you also see there that, well, 45% of the segments of the algorithm received the yuck, and only 16 of the human listeners. So there's a big difference, but still there's a lot of moments where the listener, the human listener, also is perceived as non-human. Well, we can look at certain things, and one of the things that we can do is not look at these two algorithms, not look at the human versus machine, but take them together and see what kind of characteristics determine when the speaker thinks it's not human anymore. So we get these two graphs. So on the left you see the segments that received the yuck, that were seen as non-human. On the right you see the ones that are not yucked, so that are human. You see on the left, if we look at the number of backchannels per minute, there are a lot of segments that have a very low number of backchannels per minute, between 0 and 2 per minute, so every 30 seconds max. There is also quite some that have 10 or more than 10, which is basically this. So there's a high rate of backchannels per minute. And you see here that the pattern is different. So you see a lot of them just receive between 4 and 6 backchannels, and then they're not yucked. And then if we then look at the sources, then almost 75%, so almost 3/4 of the time, the backchannel, when there was no backchannel, it was because of the algorithm. And it was because the threshold was so high that there would never be a backchannel performed. So the algorithm would always be silent. And also the 10 plus setting was also mainly due to the algorithm. So in conclusion, there is no single threshold for all speakers that is optimal. So actually we have to do some adaptation in this. So that's not a question mark, that's actually what we should do. So, final summary. We present an evaluation framework for behavior synthesis. It is, in our case, for listening behavior, very specifically back channels. We use the switch between a human and a machine, which allowed us to record this kind of behavior without a bias. And we looked at quantity and timing. And the tool can also be used to collect data, since we have the key presses, so we can retrain our models and eventually do better than we do right now. So, in a case study with back channels, we saw that the number of back channels is important to the perception. We knew that already, but now we could also verify it in an online setting. And there's much more analysis needed on these data, so we have to look at timing more deeply. We have to look at the consistency of the back channel behavior. What happens if sometimes he is nodding a lot and then not? So we have to see if this also matters for the perception. Also, we have to do offline analysis. So if we recorded everything, we can have people look at it and say, hey, do you think this is human or not? So the speaker is only one person who's now judging the behavior, and we can have many more people look at it. And also more experiments are needed. So right now we look just at back channels, only at nods. So we want to look at more back channel types. We want to have vocalization, we want to have smiles. And eventually we want to have other, also continuous modalities there. So we want to have head movements, we want to have facial expressions, we want to have gestures. And this is challenging, because if we have to interpolate between facial expressions, we might have to go from a smile to an angry face, and that requires some interpolation there. So there's some challenges ahead. And here, this is what happens if you have a threshold that is too low and you have too many back channels. So you can see what happens to the perception.
First match. Society's fault or one man's cry for help? What are you talking about? I wanted her freaking money. What the hell's wrong with him?
Okay, this is actually what we sometimes saw the algorithm do. So there's a lot of room for improvement. So the final part is the opportunities and challenges ahead. So we discussed quite a lot of things. So first of all, there are some opportunities and challenges in the observation, so in encoding the speaker. So we need robust real-time observation, and we kind of addressed it a little bit, but we might go beyond that. So if we're looking at speech, we might look also at semantics of what's being said. And one of the things that we're looking into is keyword spotting. There might be certain words that cue back channels, such as right or yeah. If we can automatically detect these, and we can detect these quite quickly, then we might use this to predict when a back channel should be given. Also, we want to include gaze. In our online observation, we did not include gaze because we could not track it robustly. But probably with some computer vision methods, we might be. Also, we want to look at facial expressions, and I will show you that we are doing this right now. We want to look at frowns and smiles, because they can be seen as back channels, but also might cue back channels. And also body pose, body movement, gestures. All these kind of things might be informative, and they should also be used in the observation of the speaker. So this is a movie that was made by my colleague just yesterday, and it shows from an observation point of view what we can do right now. So you see that the movements he's making on the left are copied onto the virtual human. There is some delay there, and not everything is being copied. The only thing that actually is being copied are the action units related to the frowning and also to the smiling. So you see also that the head movement is mirrored. But eventually, if these are slightly more robust, and if we have maybe some smoothing on certain of the modalities, we could get something that could actually be transferred to a speaker. So this is something we are working on right now. Okay, from the modeling point of view, from the, let's say the machine learning point of view, we have to really address the fact how to deal with samples that are not pure positive or negative. There was always samples or moments in time that they correspond to that are better than others. How should we deal with this? Is this black or white machine learning just good or negative? Is it good enough? Or should we have some more of a regression type of thing? Another thing is that we should look at temporal things. So right now we encoded the temporal nature of the features, so of the moments of the context, into our features. And we might do that in a temporal way. And maybe state space models might be a good way to do that because they're well understood. Also, we're gonna look at subject-specific behavior model. Not all the features might be useful for modeling the behavior of a certain subject. And also, there might be other factors at play. Then we have the generation. Definitely want to stick to online because that's the eventual motivation of our work, to have online conversations with virtual humans or robots. We want to include other back channels, vocalization, smiles. So far we have focused on nods, but we need to go beyond that and also see in what kind of context they are being made. And we need to add all these other modalities, also in the behavior of the listener. So we have to have gaze, we have to have blinks, we have to have facial expressions, body movement, all these kind of things. Right now you're just looking at a face that sometimes does this. And we need to go beyond that to really see if it works. So how far are we right now? You see on the right a virtual human that actually can do slightly better than just listening. He sometimes would say useful things, and you can see how that goes into conversation with this girl. I think it's about taking pills.
Hello, my name is Obadiah. How are you feeling today?
Hey Obadiah, I'm good, thanks. I just figured out you left like you've got a cold.
Is that so?
Yeah.
Tell me more about
You
it.
need to get some lamps, I think. Lamps are really, really good.
Mm-hmm.
Yeah. I don't really like the taste, but if you put sugar in it.
Yeah.
Sugar, yeah. Sugar's the best. And it sweetens it up, and then it tastes really good.
It can be so painful, can't it?
Oh no, Lemsip's not painful to take. Mind you, other tablets might be so. I'm not very good at swallowing tablets. Have to take like
What about when it all goes wrong?
taking tablets. Well, I don't really like to take tablets because I go wrong. Although sometimes when I get a migraine, I have to take Simple, and they're like really strong, so you'll end up with a sleep. Like I don't know, it's not like
Okay, so what you see here is that the character actually responds semantically, but basically these are just key phrases that he just puts there. This is supposed to be the depressed character, so he would only say such as, why do you feel so happy? Those kind of things. So there's not really a conversation, but he would just at a certain time put in these sentences. So if we're going to look at a slightly broader scope, what we have to do is also go beyond these speaker-listener things. So we're not only going to look at listening behavior, we have to include turn-taking. And it's going to be a big step, but we have to do that eventually to have real conversations with virtual agents, computer characters, robots. And also, what we need to do is include domain knowledge, because eventually you need to know what to say instead of just saying, without knowing what the conversation is about. Probably we'll also have to model personality and mood. You cannot have a character that is just plain static. Probably you have to have a character that is also happy sometimes, or maybe not. And we have to apply it in the wild. We have to put it in musea, we have to put it really with people on the street, we have to put it in elderly homes, we have to see how people differently than students will reply to these kind of things. And this is a nice video about actually two chatbots that observe each other and that respond to each other. I think it's hilarious. I hope you can hear it. And otherwise there's subtitles.
Hello there.
Hi.
How are you?
Great. You?
I'm okay.
That's good.
Are you good?
Yes, I am good. I just said I was.
No, you didn't. I said I was.
So you are a robot?
No, my name is Cliverbert.
Yes, you are a robot and your name is Cleverbert.
I am a robot.
Yes, I know.
Together we are robots.
I'm not a robot. I'm a unicorn.
But you said earlier that you were a robot.
I did not.
I thought you did.
You were mistaken, which is odd, since memory shouldn't be a problem for you.
I've answered all your questions.
No, you haven't.
What is God to you?
Not everything.
Not everything could also be something. For example, not everything could be half of something, which is still something, and therefore not nothing.
Very true.
I would like to imagine it is.
Do you believe in God?
Yes, I do.
So you're Christian.
No, I am not.
But you say you were not helpful, therefore you're a meaning.
Why you say idioti?
That does not make sense.
Don't you want to have a body?
Sure.
Au revoir.
So we started with a really confusing piece of conversation at the start with two children, and we end with a really confusing piece of conversation between two chatbots. I think we are at this level right now, and let's see what we can do in the future. So there's one free promotion that we'll do. There's an upcoming workshop which is exactly about these themes. It will be in Santa Cruz, so the weather will be nice, and you can surf if you're not going to the talks. It will be in September, and the deadline is early July, and you should look at it. It's somewhere advertised on the IVA website very soon. And that's it. So I would like to thank the people that did the research, and also for all the students that we bribed into participating in our experiments. That's it. Are there any questions? I think everyone understood that if there's no questions, then you can go for, yeah.
How culture differences in culture or language could affect the perceived performance of the system?
Yeah, that's a good question. So the question was, does culture affect the perception of the behavior? We expect it is. I must say that the subjects that right now evaluated all the videos are quite homogeneous. There have been Dutch students who looked at it. But we know that there is a lot of differences between cultures, especially between Asian and Western cultures, especially in the amount, but also the timing of the back channels. So there's definitely something that we should be looking into. Thank you. No more questions? Okay, thanks.